Hey everybody, welcome back. This is CHEM300, and this lecture is on the explanatory power of the quantum mechanical model. So our goals in this section are to explain the connection between periodic law and the quantum mechanical model for atomic orbitals. So thinking about the organization of the periodic table, when the elements are arranged by increasing atomic mass, elements with similar properties repeat at regular intervals or periods. And so this repeating intervals is how we organize our modern periodic table. So the modern periodic table is arranged by increasing atomic number, and it has the shape it has so that elements that have similar properties are grouped together in columns called groups. So the organization of the periodic table, its shape and the way it's laid out, is supported by both periodic law and quantum mechanical theory. So Mendelev's periodic law allows us to predict what the properties of an element will be based on the element's position on the table, right? We can differentiate where the metals and the non-metals and the metalloids are located. But Mendeleev wasn't able to explain why. All of his organization was based on direct observations of properties of the elements and then grouping the elements based on their properties that he could observe. But he didn't really understand, didn't know yet why this worked. And so that's kind of the definition of a law. A law is based on observation. You can repeat it, you can use it to predict stuff, but laws don't necessarily explain why something is the way it is. And so it's the quantum mechanical theory that really explains the why of the periodic table. And this is because quantum mechanical theory organizes things by how the electrons are arranged. So we have these groups on the periodic table of electron blocks, like the S and the P blocks, the D block, the F block, and elements in the same group, like the alkali metals in group 1A or the alkaline earth metals in group 2, they have similar electron configurations based on quantum theory. So we're kind of lining up what Mendeleev observed, grouping elements by their properties and having these named columns like the alkali metals, the alkaline earth metals, and then correlating that to like, oh, hey, on the quantum mechanical model, not only are these things based on their physical properties in these same columns, but based on how their electrons are arranged, they're also in these same columns. And so working together, periodic law and quantum mechanical theory support each other. It's like periodic law tells us kind of what to expect, like what the properties of different elements will tend to be based on their location on the periodic table. And the quantum mechanical model helps explain why. It's because they have similar electron configurations, that elements in the same column have similar properties. So if we compare our two periodic tables, one laid out Mendeleev's traditional way with representative or main group elements, transition elements, the inner transition elements are lanthanides and actinides. The shape is the same as the shape of the quantum mechanical, so to speak, periodic table, where it's laid out based on the electron blocks, these blocks of suborbitals. So the S and the P orbitals correspond to those main group elements. The D block corresponds to the transition elements. And the F block corresponds to the lanthanides and the actinides. And this works. So Mendeleev organized this periodic table based on properties that he was observing, and he put elements with similar properties in columns. The quantum mechanical periodic table is organized by electron orbitals, and elements that have similar highest energy electrons are in columns. And because it's the highest energy electrons that are involved in chemical bonding and how an element behaves, what it's going to react with, the lining up of the quantum mechanical model of the periodic table matches the periodic law, the kind of observation-based periodic table. So this is really powerful in science when laws and theories come together to reinforce each other. And that's what's happened with the periodic table as we developed the quantum mechanical model of the atom and these more complex orbitals. It was really exciting to see that this matched up with what Mendeleev had organized in the modern layout of our periodic table. So I think the periodic table is awesome, obviously. I love it. I love using it to come up with electron orbital diagrams. Like I said, you can always use that like tree where you like start at the top and then, you go down if that works for you. But I can tell you in chemistry classes, I can't think of a single chemistry class where you don't have a periodic table in front of you, either in the classroom or given as part of your test. And so if you can fill electron orbital diagrams using the periodic table method, and you can like kind of remember where these blocks are located, you will always be able to write electron configurations. You don't have to remember this tree and how to set it up, or you don't have to memorize the filling order. You can use the shape of the periodic table to guide you through the process. And that shape corresponds to the same shape as the Mendeleev's periodic table, and they work together because Mendeleev organized by properties he was observing, like reactivity and whatnot. And the electrons correspond to those same properties because it's the electrons in the highest energy shells, which all match up going down a column, that are involved in chemical bonding. Okay, so the last part of chapter 9, we're going to talk about some periodic trends on the periodic table. I'll see you then. Thanks.